All right, so this is the start of the Tcase series. Basically, this will go over in increasing detail how we went from this Tcase in the 24 to 25 race season, where we just have a simple shifting mechanism between um, these two gears and this pinion, giving us forwards and reverse, to this more complicated layout, giving us an integrated rear differential gear, the same forward and reverse selector, but on the input as opposed to the output, and then a dedicated miter box to send power to the front shaft. So to start things off, as with every project, it's best to go over the requirements. So the main requirement was to combine the transfer case and rear differential into a single housing. As you can see in this picture here, maybe it's better from this side. The motor sits on top of everything. Um, it's the only real place we can put it. And that's driven mainly by the T case here. There needs to be a certain spacing between the CVT primary and secondary here. This needs to be 8.5 inches center to center. Doesn't matter what angle it is, just needs to be the correct center to center distance for the belt to have the proper tension. So that sets the input of the T case relative to the engine. That's a set constraint. It's the same this year. So the engine sits above the T case, and then the T case is constrained in its position by the rear differential here. So there's a stub shaft that runs out of the back of the T case into the differential. It's only about 2 inches long. Um, and the reason the T case isn't sitting lower, it's spaced about 3 inches off the bottom of the car, is because we need the differential in the right spot, both for the CVs, but also so that the differential doesn't poke below the bottom of the car and end up, you know, getting hit. So the differential drives the position of the T case, that drives the position of the motor. Really pretty bad packaging, and we can't do much about it in this configuration. That's the first goal. The second goal um, kind of ties into the first. It's to improve the packaging in the rear of the car to lower the engine and transfer case. Ideally, combining the transfer case and the rear differential um, removes the primary constraint stopping us from dropping the rear diff or the T case, and that then means we should have more freedom to move the engine. But as you'll see from our final state here, we did a lot more than just drop everything. The T case and every and differential combination has moved significantly backwards, and we were actually able to pivot the engine forward and down, saving us a few inches of height there. The third criteria was to improve the location of the front output shaft to reduce the angle in the front drive line. If we scroll here to the initial state, um, is pretty abysmal. We have a really hard time getting out of this high case here under the seat. The seat sits right above this U-joint, which requires a bunch of extra HROE, hazardous release of energy guarding. Instead of needing, relatively thin aluminum sheet around a rotating shaft, you instead need 1/8 inch aluminum plate around a U-joint um, to meet regulations. So we have three U-joints here, relatively high angles on these. You have a combined over and downwards angle. I think these are both, this rear and middle U-joint are both pushing 15 degrees combined, which leads to vibration, loss of energy, etc. And these U-joints are also rather heavy. They're overbuilt for the application. The final state here, two U-joints, maximum angle is about 6 degrees. Yeah. So the last thing is reducing wear in the gearbox to improve the life and reliability. I have all the hand calcs for those that I'll go over. Um, but as you can see from our initial state pictures here, turn on the nice gold oil into a good silver color. And you can see the pinion is not long for the world. This was slightly improved last year. This image is from 2 years ago. I don't have images from this year, even though I took the Tcase apart. Um, the wear this year is more continuous along the pinion as our mesh has improved slightly, but I mean, there's 15 hours in the Tcase and basically just a knife's edge the entire way along the top of this pinion tooth. And the slop is pretty high. And then this is an image of the current Tcase box as it was freshly assembled before any testing had occurred with it. And then final state as of the recording of this first video, yeah, it's being built. The all the outer pieces, the aluminum housings have been machined, and a decent amount of the gears have been machined, but it hasn't not the shafts aren't finished, and it hasn't been assembled yet. So today I'll kind of go over how I thought about combining the Tcase and the differential, um, and I'll lightly touch on the gear calculations, just the initial sort of how much power we had out of the motor, what speeds we're looking at, and what our gear ratio should be. I actually ended up keeping the same 2-to-1 gear ratio in the Tcase, and then I bumped up the gear ratio in the rear diff slightly for two reasons. Overdrive can be helpful. Overdrive basically means your rear axle spins a few percent faster than your front axle, which can help you with rotation into turns. It can also improve your handling if you tend to have a really high understeer. Um, that extra rotation in the rear can sort of promote an oversteer behavior or lessen your understeer behavior. So yeah, um, given data I had was this graph. Um, very few data points here, but it's of the Kohler engine we're required to use in its restricted state. The red curve, you have torque relative to RPM, which drops off pretty significantly, and then you have horsepower relative to RPM. Um, we're also restricted by rules to a maximum engine RPM. The engine will do more than 3,600, but yeah. Regardless, for our gear calculations, the main thing we're interested in is max horsepower relative to RPM. Vis-a-vis, we're interested in the max torque. Torque is what kills gears. Uh, Obviously, higher RPM means higher cycles, but considering how short we are running this car between testing and comp and the other events and so on, we're putting at most 20 hours on a gearbox that just basically we can ignore fatigue unless we're talking, you know, zero safety factor whatsoever. But roughly, the CVT holds a 3.9 to 1 ratio at its minimum ratio, and then the maximum ratio is a 0.9 to 1. So this is a pretty big range, pretty high range CVT, targeted a 2 to 1 in the primary gearbox ratio, and then the existing differential ratio is a 13 to 42. I did not end up using a 13 to 42. I couldn't find the gears for it, to be completely honest. I ended up using a 15 to 48, which provides about a 1% overdrive. Um, so once again, I'm looking at the McMaster car catalog primarily. I did look at some others like Boston Gear, but the cast gears are just completely insufficient for this use case. So instead, everything comes from McMaster car. Um, the pinion gears are all hardened. It was nice to be able to find those, but the offerings of hardened pinions are pretty limited. So it was some hard work. So basically, my rough design process was to play around in Fusion with the uh, best options for how to arrange everything, and then go from there looking at how big are my gears, what ratio am I trying to achieve, what's actually available in the catalog. Um, Unfortunately, a lot of what I wanted from the catalog was not available as a hardened gear, or it wasn't available as a um, there we go, or it wasn't available in the correct ratio. So, for example, I could find the perfect pinion gear for the rear differential, and then I would just fail to find anything big enough for the actual differential gear itself. Um, which it ended up being a little bit bigger than I wanted it to be. But the strength is there. I know I'm guaranteed to never have this diff gear break or wear down, so I'm more than happy with it. Yeah, but yeah, first constraint, looking at the gears, the way I controlled all of this actually is I have an initial sketch. So this is the diff gear. I'm doing everything based on um, the pitch diameter. So you have your pitch diameters of the gear. Those are given by the gear manufacturer. Um, if you look, I have that all listed out here. So for example, for the pitch diameters of the pinions for the main gear train inputs, um, that would be right here. This is for the input shaft, the little pinion gears that ride on that input shaft. The pitch diameter is 2. The overall diameter of the gear is more like 2.25. But the pitch diameter, the diameter which the gears mesh on, is the important thing here, and that determines the spacing of the gears relative to each other. So if I look here, I have this 2-inch diameter. This is actually set as a variable, and then I've added 5 thou on top of it. Um, this is important because you don't want to design with 100% tolerance if you're, CNC machining the housing and the two shafts end up being 2 thou too close to each other positionally, and you didn't bake any tolerance in. Well, your gears probably aren't going to spin, or they're going to wear a lot before they start spinning well. So I set the pinion gear here. This is actually the idler gear, which connects to the reverse gear, the pinion gear to the forwards gear, and then right here we have the diff pinion gear, which goes to the diff gear. Um, so yeah, this is all a parametric controllable sketch. Theoretically, the entire box moves based on this, but there's so many sections that are built up on top of this that it does take some finagling for it to actually be parametric. I do have parameters, so I did a lot of the shaft diameters and the pitch diameters of the gears as user parameters that I could input to make sure I wasn't mixing anything up. And then after that, I got too lazy to use much of the parameters. But one thing I do try to do for design is I do try to set some radiuses beforehand. So I'll set a 0.25 radius as like a user parameter, and I'll actually define it as 0.26 so that you have that extra 10 thousandths that allows you to machine that much better. Because if you were to take a half-inch end mill on a radius that's set to exactly 0.25, so half-inch diameter, you'd be engaging such a large portion of the end mill that it would cause chatter. And so oversizing it by 10 thou, you go from engaging 50% of the end mill to engaging like 30% of it, 25% of it, and that's much healthier for you, and it keeps your machinist happy. But yeah, so basically I decided the gear train, and then I built it up in sections. So I built up the, ooh, Fusion's not happy about that. I built up the back of case. So this back piece of the casing here, um, this holds all the shafts, a lot of your initial bearings and everything. Then I built the middle of case, uh, where really, you're enclosing the shift portion here that runs back and forth, engages your different pinion gears. Um, Built the front of case where I hold the idler gear in. This actually took me multiple different tries. Initially, I had the idler gear on the other side of the gear train, so it could be supported from both sides. So it sat over here in this area. But I found that when I put it into the actual assembly, I couldn't get that to fit. So if you look at this primary assembly here, I'm extremely restricted with the firewall. So I have about eighth of an inch, quarter an inch between the front of the engine, which we're not allowed to modify, and the firewall here. So I can't move the engine any further forward. Um, if I were to pull a section view of the car, you would see that I can't move the T-case any further back. It's borderline already sticking out of the back of the frame. I can't really move it any further down because if I move it any further down, then I'm going to get contact between the miter box and the frame. Um, and so really I was left with the option to increase the height of the engine sufficiently enough to have it clear the top of the case, which I did want to do. That would lose almost all of our benefits to packaging and moving the center of gravity of the engine downwards. Or I could figure a new way to mount this front diff pinion or this idler gear for the reverse. So that's what I chose to do instead. This mounts into the front of case. It's a single-sided shaft, so it's a shaft supported only on one side. There's a bolt that comes through from the front of the case here. It bolts into this idler shaft. The idler shaft is retained by a heat fit into the front of the case, and then it has all the appropriate thrust bearings, and it has a roller bearing here inside of the gear itself so that the gear can free spin on the shaft since the shaft is locked in place. And then lastly, took me quite a while, but I built a miter box on the end here. It was a bit difficult getting the correct assembly order. So this miter gear has to be assembled onto this shaft after everything is, or this front of case is put on. Um, and then the miter box is assembled over top of that gear sort of as a single final piece, and then it's bolted in. So yeah, assembly, potentially a bit of a nightmare, but this is one of those things where we're not going to have to service it a lot, I hope. Um, and it doesn't run enough hours for it to need to be built to the utmost reliability. This is a very custom specific part, and so I'm not super worried about the maintainability of it. Um, if I were to go build 100 cars with this design, I probably would have made some different decisions, but for what's essentially a one-off part that maybe we make one more per year, it's all right. It's almost better than the previous year's option. Um, since this didn't have a way to properly maintain the gear mesh here, we ended up with some pretty bad wear due to flex in the case and also flex in this input shaft not being retained very well. And then the gears here weren't actually strong enough to withstand the wear, and so the gears themselves degraded. The Tcase just had an extremely finite life. So yeah, that's a rough overview. I think I will make a section on each one of the rest of my main points that I've laid out here. So especially I will focus on packaging, sort of the iterative design aspects there, and I'll do a full breakdown of all of my gear calcs, all the assumptions I made in the calculations, because there's actually quite a few. Um, for example, if you look at the calculations, I basically assumed that there was zero loading factor on the gears. Just absolutely zero concern for any shock factor. There's kind of two reasons for that. Firstly, uh, rapidly you see our um, horsepower flatline with regards to RPM and our torque really drop off. So unless we're pulling at low speeds, we're not even close to stressing the gears. And secondly, we have a CVT. The engine is connected to the drivetrain by basically a fat rubber band. So the shock loading we're going to see is pretty minimal. The last thing, I don't actually have the calcs written out here, but I whipped up some pretty rough ones. The previous Tcase was significantly undersized as far as gear strength goes. Obviously, you know, that would explain why the gear eats itself and turns our oil silver. But estimated, uh, I believe the previous gear case, the strongest or the gear mesh had a rated horsepower of about 5 horsepower. Um, and the weakest component in this new mesh is at 8.82, which is about our max. Theoretically, we get peak torque at 8.5 horsepower. So we're right on the edge, but is a solid 40% stronger than last year. So yeah, that's all I have for right now.